did you see? Something evil?
Excitement, confusion.
Okay, so question 1 in the warm-up is a proof, and it's asking us to prove that for all n, where n is a natural number, the expression n squared plus 1 is not divisible by 4. Okay, please pause the video and try this. Okay, so let's have a look at the full solution. Okay, so the first question involves the natural numbers. So I've written out the sets of natural numbers here, and we need to test each individual case somehow. Now, we can't use proof by exhaustion because there's an infinite number of them, but we can use representatives, and I can partition the natural numbers into evens and odds. So if you remember from the work we did on proof, we can actually write down any even number in the following way. So we're going to do that first. Okay, so we're going to say let n equal 2k, all right, such that k is a natural number. Now then, I'm using k as a natural number here because if I take any of these natural numbers and substitute them into this expression, I'm going to get an even number because it's going to double. So let's substitute this into our expression. Okay, so let's do that. So n squared plus 1 is going to equal 2k all squared plus 1, which is going to equal 4k squared plus 1. Now then, the first term is obviously divisible by 4. It has a factor of 4. The second term removes it from the 4 times table by adding 1, so this is not divisible by 4. So the first one checks out. Okay, now let's have a look at the next term. So we're going to, not the next term, sorry, the next case, we're going to look at the odd numbers now. So let's write down a representative for the odd numbers. So let n equal 2k subtract 1 such that k is a natural number. Alright, now if we do that, you might argue that why don't we use 2k plus 1 here? Well, we could, but I want to be precise, and if I use 2k plus 1, remember I'm selecting k from these natural numbers here. If I use 2k plus 1, the first natural number will be 1, so that will be 2 times 1, which is 2. Add 1, which would give me 3. So I would never ever get the first odd natural number. So I don't want to use that. Let's stick with this and make it really precise. Okay, so let's go through our expression. So substituting it in, we're going to have n squared plus 1 is going to equal 2k minus 1 all squared plus 1. Alright, let's expand that. So that's going to give us 4k squared, subtract 4k, plus 1, and then plus the extra 1 on the end. Okay, let's just tidy that up. So that's going to give us 4k squared, subtract 4k, plus 2. Alright, now we can see clearly we can factor 4 from the first two terms. Okay, so let's just do that. So that's going to give us, my nails are going to rub it out, 4, and then brackets k squared, subtract k, okay, plus 2. Alright, now we're done. So 4 is the factor in the first term, so the first term is clearly divisible by 4, but by adding 2 that removes the divisibility of 4, so we're finished. So question 2 is asking us to evaluate the limits of a sum, so please pause the video and try it. Okay, so what are we being asked to do? Well, if you are familiar with the specification and the recent past papers, you'll notice that this is actually the definition of the definite integral of y equals x squared between x equals 1 and x equals 4. And we can see this in the following video demonstration. So this is showing that as n, the number of rectangles, increases, the width of each rectangle, delta x, decreases and approaches 0. This is the limiting behaviour. And we can also see that the sums of the areas of all the rectangles approximates better and better the exact area under the curve. Okay, so let's have a look at the full solution now. Okay, so we're integrating from 1 to 4, and it's the function x squared with respect to x. Okay, so this is straightforward year 1 integration, so nothing scary about this. So let's just write it out. So we're going to have equals, okay, big square bracket, and remember we add 1 to the power and then divide by the new power. So that's going to be x cubed over 3 evaluated between 1 and 4. Okay, so let's give myself a bit more room here. So let's use the curved brackets now. So we're going to have 4 cubed over 3, close that, subtract 1 cubed over 3. Alright, we can evaluate that pretty easily. So 4 cubed, use your calculator if you need to, but we should all know that's 64 over 3. Subtract 1 cubed, which is 1 over 3. Okay, and that's going to give me a final answer of 63 over 3, which actually simplifies nicely to 21. Okay, and we're done. Okay, so question 3a is asking us to differentiate with respect to x the product of x and the natural log of x subtract 1. So please pause the video and try it. Okay, great, so let's have a look at the full solution. Alright, so what I've done first is I've said let y equal x multiplied by log x subtract 1. Now it's up to you here. You could actually multiply this out if you wanted to. I'm not going to do that. I'm going to use the product rule directly without multiplying it out first. So we can see here we have the product of two functions. We have x and log x subtract 1. So as you know from class, I'm going to just label those. This is just so we can use our little technique, our shorthand. So that's going to be 1. That's going to be the x. Okay, and then the log x minus 1, that's going to be my number 2, my second function. Alright, so let's just make a list of everything we know. So my function 1 and my function 2, which I'm going to do what I've done in red there. Okay, so let's just make a note of what they are. Get my black pen, red pen. Okay, so that's going to be x and log x subtract 1. Okay, this is just a shorthand. Okay, let's do the derivatives. So the derivative of x, we should all know that, that's just 1, isn't it? So let's just write that in. So I'm going to call it d1. Okay, and I'll put d2 there. I'm not as quick as black pen, red pen with the switch, mainly to do with the furry hands, I think. So my d1 is just going to be 1. Now, and remember, the derivative of the natural log is 1 over x. It's a standard derivative. And if you differentiate -1, obviously that's 0. Okay, so now we have all the ingredients to use the product rule. So I'm just going to make a note that we are going to use the product rule here. All right, so product rule. Okay, so remember our shorthand way was we start off with the second function, 2, and we multiply it by the derivative of the first function. Okay, and then we add the first function multiplied by the derivative of the second. Like so. And remember, this technique helps us also with the quotient rule because there's less to remember. Right, okay, now let's get to the proper working out. Let's find our derivative. So, dy by dx. So that's going to equal, so let's put all the ingredients together here. So we've got the second function, which is 2, so that's going to be ln x subtract 1. Okay, and then we're going to multiply that by the derivative of 1, which is 1 up there. So multiply by 1. And then I'm going to add the first function, which is x up there. And multiply that by the derivative of 2, which is 1 over x. There we go. Right, let's just tidy this up now. So the first part is just multiplied by 1, nothing to do. So that's going to be ln x subtract 1. And then we have a cancellation of x, so that's going to be plus 1. And this is an interesting result, isn't it? So we just get the natural log of x back. Okay, and we're done. Just make a note of that. That's an important result for later. Okay, so this time we have to differentiate with respect to x the natural log of the modulus of sec x. Okay, so please pause the video and try it. Okay, and let's have a look at the full solution. Alright, so in this question we're asked to differentiate the natural log of sec x. So notice we've got the modulus signs here. Now this is a precaution because the natural log of a negative number does not exist. There are no real solutions for that. So because sec x can actually be negative, we have to take this precaution and put the modulus sign to make sure this is well defined. So we're going to differentiate it, and in order to do that we notice that we have a function sec x within another function which is the natural log. So this is the chain rule. So we're going to write down what our u is going to be, and the u is always going to be the function within the other function. So let's just state what u is. So we're going to say u is equal to sec x, like that. Alright, now because we've stated u equals sec x, we can now rewrite y as follows. Y equals the natural log of u. I'm just going to drop the modulus sign for the time being. Okay, so now we are ready to differentiate. So if you remember from the chain rule, we're going to differentiate u and y separately first. Alright, so let's do that. So du by dx first of all. So du by dx okay, now sec x is a tricky one if you want to do it from scratch, but you may remember that this is a standard derivative that it features in your formula booklet, so we can just write that down and just look it up if you're not convinced. So that's going to be sec x again tan x, and it's a nice exercise to derive that for yourselves. Okay, and then we have to differentiate y with respect to u. Okay, so that's going to give us dy by du. Really should cut my nails, it's hard to write these. Okay, dy by du, and that's going to be 1 over u. Alright, Now, to finish off, we're going to put our two results together to find dy by dx. Okay, so let's write it out in full. Alright, so dy by dx is going to be equal to the product of our two derivatives. So that's going to be du by dx multiplied by dy by du. And notice that the du's will cancel in effect. You shouldn't really think like that, but it looks as though they will, and that will give us the dy by dx. So we just multiply the two derivatives together. So that's going to be sec x tan x multiplied by 1 over u. And I'm going to sub in what our u is. Remember, our u was sec x. So that's actually going to be 1 over sec x. Alright, now then, we've got some nice cancellation here. So if you'll notice, we have sec x in the numerator and the denominator, so that's going to go with that. And we are left with tan x. Alright, now that's rather nice. So we know that the derivative of the natural log of sec x, within the modulus of course, is tan x. Now that gives us some more information. We can actually write something else down here, or what I could do is I would like to rewrite this because it's going to feature later on in the lesson. Alright, so what we've been told, or what we've just deduced, is the following. So we now know that the derivative with respect to x of natural log of sec x inside the modulus of course is just tan x. Okay, so just bear that in mind. Okay, and we'll stop there. Okay, so the final question in the warm-up is a binomial expansion, and it's the first three terms of 1 over the square root of 9 minus x, and you're also asked to state the range of validity for x. Okay, please pause the video and try this. Okay, so the following video will combine parts A and B. So this is question 4 in the warm-up, and it's a binomial expansion. We're asked for the first three terms. And it's a year 2 expansion because we have a negative fractional power. So the expansion form we're going to use is going to be the 1 plus b to the n. This is the one I gave in class. It's not quite the same as the one in the formula booklet, but I'll explain more about that later. So our first task is to force the first term in our linear bracket here to become a 1 so that we can use this expansion. And remember, we are trying to expand 9 minus x to the power negative 1/2. So I'll write down the bracket and let's see what we can do with it. So it's going to be 9 subtract x, like that. Now, if I want to force that to become a 1, then I simply have to factor out the 9. Okay, so that's going to be 9 multiplying 1 minus, or 1 subtract, sorry, x over 9. And if you multiply that out, you'll get the 9 minus x, so they're equal. Okay, and in this question, we are raising the 9 minus x to the power negative 1/2. Okay, so let's do that. So I'm going to put brackets around this. Okay, and I'll use big square brackets for this. Okay. Now then, we have to realise that both the 9 and the 1 minus x over 9 are being raised to the power negative 1/2. So that's what I'd like to do. So let's do that now. So it's going to be 9 to the power negative 1 over 2, multiplying 1 minus x over 9, to the power -1/2. Okay, and we can do even better because we have 9 to the power -1/2. Remember, this came up in the probably the very first week of your course. We can write that quite simply as 1/3. Okay, so the negative part of the power means that we can write it as a reciprocal, so it would be 1/9 to the power ½ which is 1/3. Okay, so let's just finish that off. So we can do even better now. We can say that would be 1/3 multiplying 1 subtract x over 9 to the power -1/2. Oh, it just fits on. Excellent. Right, so let's carry out the expansion. Okay, so we should have plenty of room here. So let's write it out. So 1 over the square root of 9 subtract x. We have just discovered it's exactly the same as this, what we've just worked out here. So I can now apply the binomial expansion. So it's going to be 1/3, and I'll open a big bracket and we will use the expansion here. Okay, now one thing I haven't mentioned is what the b and the n are going to be. So as you remember, I've reinstated the b from the original binomial expansion, which was a plus b to the n. Okay, and I do that because when it's written as 1 plus x to the n, there can be some confusion. Do I substitute in x or do I substitute in something else? I mean, we have to be clear. Okay, so the b is going to be the -x/9. So let's write down what n and b are going to be. I'll make a note of it here. So n is -1/2 because that's the power, and b is -x/9. So I just replace the n and the b wherever I see them in the expansion. Okay, so the first term, straightforward. 1, okay, no problem there, plus, okay, now n is -1/2, so I'll put that in. Alright, and then we've got the b, so that's -x/9, okay, and that's going to be divided by 1 factorial. Okay, and then for the third term we do add -1/2, okay, and then it's going to be n minus 1. So very quickly, -1/2, subtract another 1, that's going to give us -3/2. Okay, so that's the n and the n minus 1. That's divided by 2 factorial as the pattern continues, and then we have, and this is the bit you've got to be very careful of, -x/9, which is b, but this time it's squared, plus the order of x cubed, which we're not interested in today. Okay, so it's 1/3 multiplying all that. Do not forget the 1/3 at the beginning. Okay, so this expansion is going to be equal to 1/3, so let's just tidy up each of these terms now. 1/3, 1. Now, that's going to be a positive term because we've got a negative and negative. So that's going to give me positive x/18. Okay. And then we have another positive term here, and it's divided by 2 factorial. So that would give me positive 3/4 divided by another 4, so that's going to be positive 3/8. Okay, and then I will just square the -x/9. So it's all positive, isn't it? The negative squared is positive, so that's going to be x²/81 plus some other terms. There we are. Okay, now let's finish this. Let's multiply through by 1/3. So the expansion is going to go 1/3 plus x/18 times 3 is 54, and then the 3's will cancel. There's a 3 in the numerator and there, so I have to multiply the 8 and the 81 in the denominator, and that will give me 648. X squared over 648. Okay, plus some other terms. Now that's the final expansion. Okay, now for the range of validity, this is also given in the formula booklet, but I'm going to write it out using the B terminology that I instated earlier. So if we have a binomial expansion in this form, it is only valid if your B is absolutely less than 1, strictly less than 1 in the modulus. Okay, that's how you'll see it written, but you might be more familiar with writing it like this, or maybe more comfortable. So B has to be between -1 and 1 for this to work. Okay, otherwise you'll get a diverging series. So if we replace the B with negative x over 9, okay, and then just a little bit of manipulation, so that's going to give us -1 and negative x over 9, which is strictly less than 1, and then all I have to do is multiply everything by -9 essentially, and you can check this. I won't do any more working out, but your x will be between -9 and 9. Okay, and I'll stop there. So in the next few slides, I'm going to set up the idea of integration by parts using an example. Okay, so our aim, as we know, is to integrate x squared x. And you may be wondering why the first thing we need to do is to differentiate x tan x. Okay, well, all will be revealed, so don't worry about that. So let's just go ahead and do it. And in fact, it would be a good idea if you just pause this for a second and maybe tried it yourself, and then we'll check answers in a moment. Okay, right, let's have a look. So if we look at this derivative here, it's x and tan x. That is clearly a product rule question. We have two functions, x and tan x, multiplied together. So I'm going to label them 1 and 2, as is customary. Okay, I hope you can see that. So let's just write out what information we have. So we have 1 and 2, like so. And let's just write down what 1 is again. So 1 is the function x, and 2 is tan x. Alright, so now we just have to write down what the derivatives of these two functions are. So we'll call this d1 and d2. Alright, nothing too onerous here. These are both standard derivatives. So x, as you know, will just differentiate to 1, and tan x, as we saw earlier, I think in the differentiation chapter, differentiates to sec squared x. Okay, right, so we've already mentioned this is a product rule, so let's put our derivative together. Okay, so dy by dx now, so dy by dx. Okay, and I'm just going to write the shorthand version of this, just to remind you. It's always a good idea just to write down as many steps as you can, as well as you need to, just to remind yourself what you're doing and get into a rhythm. So it's 2 multiplied by the derivative of 1 plus 1 multiplied by the derivative of 2. Okie dokie. Right, so let's just fill in what we know. We've already done this work, so it's just a case of putting it all together. So 2 is tan x multiplying d1, the derivative of 1, which is 1, plus first function, which is x, multiplying the derivative of 2, which is sec squared x. Okay, let's just remove the multiplication symbols, I suppose. So that's going to equal, it's our final step, tan x plus x sec squared x. Now this is interesting because we have got the x sec squared x that was stated in our aim. Okay, so more about that in a moment. So let's see what we can learn now from this result. So I want to state first of all, we'll talk about the result from question 3b in the warm-up. Now we differentiated the natural log of sec x, as you can see here. Now what I would like to do, and I said earlier this would be an important piece of information, when you write down a derivative you automatically get another piece of information. I can actually write this as an integral also. So imagine if I differentiate the natural log of sec x to get tan x, then if I integrate tan x, that must give me the natural log of sec x because it is a reverse process. So why don't we just write this down? So the integral of tan x dx is equal to the natural log of the modulus of sec x and plus the constant of integration. Okay, now in a sense it's as though we have just integrated both sides of this. So you can imagine I've basically just stuck integral signs on both sides, and the integral of a derivative just gives you the function back, and I have the integral of tan x on the right hand side. So that's an important piece of information we're going to use. Now back to our aim. We want to integrate x sec squared x. Well, we just had a result a moment ago. We just discovered that if we differentiate x tan x, the x sec squared x appears in our derivative. So I'm just going to write out the result in a similar way as this green statement here. So let's just do that. So we know that the derivative d by dx of x tan x is equal to tan x, all right, plus x sec squared x, like that. So you may be wondering why I've left gaps. Well, you'll see in a second. Okay, so what I'm going to do with that statement is I'm just going to integrate the whole thing. Okay, we want the integral of x sec squared x. Okay, I can integrate the whole thing, and integration is a linear operator, so I can do it term by term on the left and the right. So I'll do them in red. So if I integrate both sides, I get the integral of all this with respect to x, so I put my dx in there. Okay, that's going to equal the integral of tan x dx in there, okay, plus the integral of x sec squared x dx. They are identical statements. So the thing I want is on the far right. So what can we do with this? Well, let's look at the left hand side. We have an integral of a derivative. Now I've just said a moment ago, and we've just demonstrated this, if I integrate a derivative it effectively gives me the function back because they are reverse processes. It's like an inverse function. So this is just going to be x tan x because I'm integrating the derivative of x tan x. Okay, so we can just write that down straight away. So that's no work at all really. So x tan x. Okay, so that's the left hand side sorted out. And that's got to equal the integral of tan x. Now, let's just pause for a second. The integral of tan x, that was our result from question 3b, right here. We know the integral of tan x. I'm just going to write it in. So it's the natural log of sec x with the modulus sign. Like that. Okay, so it's come straight from here. Okay, and then plus the thing I want. So I'll just leave that as it is. Okay, so plus the integral of x sec squared x dx. My wife will wonder what I'm talking about. Hope she can't hear me. Okay, now let's rearrange this. Okay. Oh, just one thing to bear in mind as well. Because we are integrating, there will be a constant of integration. Okay, that will come in the last step. So I'll just put that on in a moment. I say I haven't forgotten about that. So rearrange, and then let's see what happens. So if I subtract the natural log of sec x from both sides, we get x tan x. Subtract the natural log of sec x. Okay, and that's going to equal the integral of x sec squared x dx. Okay, and I should put a plus c on there as well. Okay, and that's the result. Okay, now where did that come from? Obviously I can't just pluck these things out of thin air. How did I know that I needed x tan x in the beginning? Okay, well, all will be revealed in a moment. Now we're going to generalize the result. Okay, so this time we're differentiating two general functions of x, u, and v. All right, and it's the product of u and v, so it's the product rule, so we number them 1 and 2. So u is going to be 1 and v is going to be 2. Right, so let's state the derivative, and there's nothing to actually differentiate, we just write them in their general forms. So dy by dx is going to equal, we've done this a few times now, so that's 2 multiplied by the derivative of 1 plus the first function 1 multiplied by the derivative of 2. Okay, so let's just write those in. So function 2 is v, so that's v, and the derivative of 1 is just going to be du by dx with respect to x, of course. And the first function is u, so that's plus u, and the derivative of 2 is dv by dx. So we've actually stated the product rule properly. Okay, so what are we going to do with that? Well, we'll find out in a second. So now let's replicate what we did in the previous example. Okay, so for the next part, I've just restated the product rule here, and just to remind us, y is of course uv, the product, so I've reinstated u and v into this term here, so it's as it was stated in the question, d by dx of uv. And we've got the product rule on the as it was written previously on the right hand side. Now there are gaps, of course, because as we saw in the example, we're going to integrate each term. Okay, so let's write in the integral symbol all the way across. So it's going to be the integral of d by dx of uv with respect to x, so there's a dx on there. Okay, and we're going to integrate term by term. Like so. Alright. Okay, so remember from the previous example, it was the term on the far right that we wanted. So we're going to keep that as well. I think we'll stick with that idea. So we're going to make that the subject of our equation. And let's just have a look to see if we can do any simplification. Now, if you look at the term on the left-hand side, we have got the integral of a derivative yet again. So I can just as easily state this as uv, okay, because the integral and the derivative undo each other. They are inverse operations in a sense. Alright, so this is just going to be uv. Okay, I think I'm molting. And that's going to equal exactly the same on the right hand side. So it's the integral of v du by dx plus, and my green line's in the way, that's plus the integral of u dv by dx. I think I've scratched out my dx as well, but never mind. Okay, so let's just rearrange this. So I'm going to start with the u dv by dx. I'm going to keep that where it is, and I'm going to subtract this term from both sides. So what I'm going to get in the end is the following. And I forgot the dx on there as well. So it's u dv by dx, because it's an integral, is equal to uv. Okay, and then I must subtract the integral of v du by dx. Okay, now this is extremely important, and I strongly recommend in your notes you make this look as important as possible, because this is the integration by parts process that we're going to apply in our next examples. Okay.
You have survived barely, but you must now do the worked examples.
So in our first worked example, we're going to integrate x cos x with respect to x. Alright, so this is the first worked example on integration by parts. So what I've done is I've written out our integration by parts process up here. We're going to refer to this constantly throughout these worked examples. And the first thing to do is to let capital I for integral equal our question, which is the integral of x cos x with respect to x, which is the dx here. So our first task is to decide which out of the x and the cos x is going to be the u and the dv by dx. So we think of it like the product rule. Okay, the product rule, we're talking about u and v as the product of two functions. It's the same idea here. We want x and cos x as our product to represent u and dv by dx. Now there is a thought or there is a theory behind this, okay, to make things easier and actually so you can actually integrate them. What you should do is choose your power of x, whatever it is, to be your u. Now the reason is because you're going to be integrating later du by dx, and we need that u to simplify. We want something that we can integrate easily later. Alright, so as you know, when you differentiate powers of x, the derivative is one power less, okay, so in essence it becomes more and more simple. Cos x is a transcendental function, so it's just going to alternate between sine and cos, and it will change sign depending on what you're doing, but integrating or differentiating will not change this very much at all. So let's write down what our u and our dv by dx are going to be. So that's our first job. So I'm going to do that here. A little aside. So u is going to be x. Okay? And I'm going to write dv by dx here. Okay? And that's going to be cos x. And that's our first product inside the integral. So what we need to do now is to write down what du by dx is first of all, and what v is going to be. So du by dx, that's straightforward, so that's going to be du by dx. Okay, so you just differentiate u, which is just going to be 1, okay, because the derivative of x is just 1. Now here we're going to write v. Now v is the integral of cos x, okay, and that's standard. So you should know, without looking it up, hopefully, that the integral of cos x is in fact sin x. So there it is. Okay, so now we have all our ingredients, so we can now actually go and integrate x cos x using the by parts process. So let's do this. So I'm going to refer to it as I. Alright, and we sub everything in, so it's going to be u times v first of all. This is the first term in our right hand side expression. So uv, so that's going to be x multiplying sin x. Okay, and then we're subtracting the integral v du by dx. Now du by dx is 1, that's okay, and it's the integral of v, so it's just going to be sin x. Alright, so that's what our I is going to be. Okay, so we have to perform this integration. Now again, that's a standard integration, so let's do that. So it's going to be x sin x. Okay, now because it's if I just ignore the sin x, sorry, beg your pardon, if I ignore the negative first of all and just focus on this integral of sin x here, we should know that the integral of sin x would be negative cosine x. Okay, so I'll just put that in a bracket just so we're clear. So that's going to become negative cosine x. Alright, obviously there will be a constant of integration, but I'll add that at the end. Just check that if you're not sure by differentiating. Okay, so just to finish off, so we're going to have x sin x. The double negative becomes positive, so that's going to be plus cos x, and then we can add our constant of integration. Okay, and we're finished. Now what you could also do now, it's a nice exercise, is just to check by differentiating that you do in fact get x cos x that we started with, but I'll leave that to you. And for part B, we're going to integrate x cubed multiplied by the natural log of x with respect to x. Okay, so now we're going to look at the integral of x cubed natural log of x as a product. Now, I said in the previous example, and this was a very important point, that when you're choosing your u and your dv by dx, what you should be doing is choosing your u to be the power of x. Okay, usually, as a bit of a giveaway here, there will be a power of x that you'll see within your integrand. Okay, simply because when you're doing this bit over here, you're integrating v du by dx, you'll be integrating a more simplified version of this. So when you see an obvious integration by parts question where you have a product and the second function is something like sine x or cos x or e to the x, something transcendental, you should always choose x to a certain power as your u. Now, this question here is the only exception, okay? This time, because we have the natural log here, this is what your u should be. You should choose your u to be ln x. And you'll know this because when you differentiate the natural log of x, you get 1 over x. And that creates simplification in the integrand over here. Alright, so with that sorted, let's write down our 4 functions that we're going to be subbing in on the right hand side. Okay, so the first one we're going to write down is our u, which we've just decided is going to be the natural log of x. Okay, the second thing which we automatically know because we've decided that is that dv by dx is going to be x cubed. Okay, right, that means that we can now, again, just following on from what we've just written down, we can now write down du by dx and v. So let's do that. So du by dx, try not to rub it out. Okay, so that's going to be 1 over x. There it is. And v, we integrate, we'll do this in our heads, we integrate x cubed. So remember, that's classic or year 1 integration. So add 1 to the power and divide by the new power. So that's a quarter x to the power 4. Now we're ready to go. So let's substitute everything into the right hand side of our integration by parts formula or process. Alright, so let's write down what our I is. Capital I is going to equal, so it's going to be uv, so it's the product of the u and the v, ln x and x to the 4 over 4. So I'll put the x to the 4 over 4 first. Alright. Okay, and then we subtract the integral of v du by dx. Right, so let's just do a little bit of a side work here. If I want to just multiply those two functions together, so it's going to be x to the power 4 over 4 multiplied by 1 over x. Now notice there is cancellation, so the x in the denominator goes and that reduces. I should have just crossed out the 4, but never mind. So it's x cubed over 4. Alright, so that's nice. So let's just write that in. Okay, and that's dx with respect to x. Alright, so we have to perform our integral, our integration. So that's going to be x to the power 4 over 4 ln x, subtract the integral of this. Again, this is year 1 integration, so add 1 to the power, divide by the new power. So I've got to have x to the power 4, and then remember I'm going to be dividing by 4, and the product of 4 and 4 is going to be 16 plus the constant of integration. Alright, and we're finished. Okay, so now we're going to move on to question 2, and we're integrating for part A x squared e to the x with respect to x. Alright, so for worked example 2a, we are asked to integrate with respect to x, x squared e to the x. Okay, so I've set I, capital I, equal to that. So we have to do our preliminary check. What is our u going to be? So there is no natural log of x in here, so we have to use a power of x as our u, so it's going to be x squared in this case. And remember, this will force our hand, and we can write down what dv by dx is as well, which will be e to the x. So let's go straight ahead and write that down. So my u is going to equal x squared, and my dv by dx is going to equal e to the x. This is one of those topics where you need to make sure your u's and your v's are distinct. Okay, now let's write down what du by dx is and v using differentiation and integration respectively. So du by dx goes in here, so simple year 1 differentiation, that's 2x. Alright, and then my v, nothing simpler than to integrate e to the x, because we just get e to the x again, which is nice. So we've got that. So our ingredients are ready, our little aside is finished. So let's go straight to using integration by parts. So I'll just cordon that off. So let's do it. So I is going to equal uv, so that's x squared e to the x. Subtract. Now what I'm going to do is I'm going to bring the 2 out to the front of the integral. Okay, and you'll see why in a second. So I know it's 2x e to the x, but I'm just going to bring the 2 out. So 2 lots of x e to the x dx. Okay. Right, now you may notice a slight problem. We have got a situation where we are going to have to use integration by parts twice. So we've done it once, but we now have the product of x e to the x, which also requires integration by parts. So what I'm going to do, I'm going to call this I1. Alright, and we're going to have to do a little bit of side work again before we can go back to our final answer. So I'll do all that at the bottom. So we'll call this is the I stuff here. And then I'll do the I1 stuff underneath. So for I1, in fact, I'll just partition that as well. So for I1, let's have a look. Well, my u, again, it's very simple. It's going to be x in this instance. So the power of x has dropped by 1. So my dv by dx, again, is e to the x. No worries there. All right, so I can instantly write down my v. That's also going to be e to the x, no changes. And my du by dx, got really carried away then, so I didn't switch pen. Sorry about that. So I differentiate that, that's going to be 1. Alright, so I've now finished that block. So this is, or these are my ingredients for I1. Alright, now we're going to write this out properly. So for our second step, I is going to equal x squared e to the x, subtract 2 lots of, now we're going to apply integration by parts here again. I'm going to open a big square bracket, and then I'm going to put in the I1 stuff. Now remember, I1 is going to be uv, but u is x this time. So that's going to be x e to the x. Okay, and then subtract the integral of v du by dx. Alright, so that's going to be e to the x multiplied by 1. Now that's much better, isn't it? We don't have any problems integrating e to the x. We've just done it twice already. Okay, so that's dx there. Okay, and I'll close my big square brackets. Okay, so that's the I1. I apologise, I've been very inconsistent with this. I've switched from green to red, but I'll just label that as I1 there. Okay, so we've got a couple more steps to finish this off. Alright, so my I is now going to equal x squared e to the x, subtract 2 lots of x e to the x, that's multiplying through the bracket, and then I've got to multiply my integral here by -2. Now that's a negative integral, so that's going to become positive because of the double negative. So that's plus 2 lots of the integral of e to the x dx. In fact, that doesn't look much like an e. I'll just do that bit again. That better. Okay, so now we've done that bit. So again, integrating e to the x does nothing, so the next step is quite straightforward. So that's just going to equal, or I is going to equal x squared e to the x, subtract 2 lots of x e to the x, plus 2 e to the x, and then plus the constant of integration. Okay, and we're done. Now you might want to check this. There's no like terms to collect together, they're all distinct. You might want to actually use differentiation to check that when you do differentiate this, you do get back to x squared e to the x. Okay, that's a nice exercise for you. Okay, but we'll stop there. And for 2b, we're going to integrate e to the x sine x with respect to x. Okay, so for 2b, this is one of my favourite examples of integration by parts. We are going to integrate with respect to x, e to the x sine x, both transcendental functions. So we haven't got a u, which is a power of x, or a natural log of x to choose from, but we have to choose something because it's a product. So let's just try this out, okay? I don't know if this is going to work, but let's choose u to be e to the x. Alright, so let's do that. Okay, now this forces me to write down dv by dx to be equal to sine x like so, and we can also write down the du by dx and v using differentiation and integration. Okay, both standard results, so no worries there. So let's just write those in. So du by dx is just going to be e to the x because it's its own derivative by definition. Okay, and then v is going to be, well, if we remember, the derivative of cos x is negative sine x, so we reverse that, so the integral of sine x must be negative cos x. Okay, just enough room there. So there's our aside done. We've got our ingredients to do integration by parts. I'll just partition that off, ready to use. Okay. And this is all the I stuff, isn't it? So I'll just label that as I, just in case. Okay, so let's go back to our question and let's integrate. Okay, so I is going to equal, so it's the product of u and v, so that's going to be negative e to the x cos x, just putting all those components together. Okay, and then I subtract the integral of v du by dx. Okay, now v is negative cos x, du by dx is e to the x, So I'm going to have a double negative, so I'm just going to put that as e to the x cos x dx. All right. If you need to do an extra step there, please do so. Okay. But we have a double negative and we're subtracting, or we have a negative and we're subtracting, I should have said. All right. Okay. So we have to do yet another integration. So another integration by parts. We have another product of transcendental functions. So I'm going to call that I1, and we're going to set up the ingredients for I1 in the bottom left corner. Okay, so this is going to be I1. All right, so let's do that. So we just specify our U and our V. So I'll do the same thing again. I'll say U is e to the x. Just do that again because you probably can't see that. I'm just close to the edge there. Okay, that means that dv by dx must be cos x in this case. Okay, and remember our hand is forced, so we need to write down du by dx as identical to the previous part. So du by dx equal to e to the x, and v is the integral of cos x, which is sin x. Okay, so these are our ingredients for I1. Okay. And I'll just cordon that off as well. Right, so we can do our working out on the right hand side. So we're going to have to use integration by parts again. So let's do the next step in full. So I is going to equal negative e to the x cos x plus, now I'm going to open a big bracket and I'm going to do my integration by parts for the second time for I1 in the large bracket, in the square bracket. So it's u and v, so that's going to be e to the x sin x this time. Subtract the product, sorry, the integral of the product of v du by dx. So that's going to be the integral of sin x e to the x. Now I'll put the e to the x first again, just for consistency. And that's dx. Hopefully I just squeeze on. We're tight for space, aren't we? I'm just going to squeeze on those square brackets. Hope you can just see that. Okay, so that's the I1 integrated. Now you'll be thinking, but we're going around in circles. We have to do yet another integration. Okay, now you're right, but there is a twist. Now I'll just write out the next step. Let's just get all the terms together and see what we've got left over. Okay, so my I, capital I, is going to equal negative e to the x cos x plus e to the x sin x from I1, subtract the integral of e to the x sin x dx. Right, lots of terms and an integral on the end. Right, am I going to have to use by parts again, and is this just going to go on forever? Well, no. Look what we have here. We have e to the x sin x. Does that look familiar? It's integrated. Okay. It was what we stated as our I right at the beginning. So I can just replace that integral with I. Okay, so let's do that. plus e to the x sine x, subtract capital I. Okay, remember I is our goal. We want to find out what I is. Now, if you look at what we've got here, we've got I on the left and I on the right. If I add I to both sides, it will remove the capital I from the right hand side. So that's going to give me 2i is equal to negative e to the x cos x plus e to the x sine x. This is exciting, isn't it? That's got to be my favourite step in the whole process. So okay, so we've almost got I. Now all I have to do now is divide by 2 and we're there. So big capital I is going to equal, and I'm going to rearrange this. No, I won't. I'll leave it as it is. Okay, so it's going to be negative e to the x cos x plus e to the x sine x all over 2. And we're done. Isn't that amazing? Okay, we'll stop there. And don't forget the plus c. And now for the final worked example. So in the final example, we're looking at the curve y equals x squared multiplied by the natural log of 2x. And the diagram shows a bounded area R, which is bounded between the curve itself, the x-axis, in particular between the points x equals 0.5 and 1. So without saying it explicitly, the question is just asking us to integrate the curve y between 0.5 and 1. So let's just state that, and we can write that down as our area R that we wish to find. So R is simply the integral between 0.5 and 1 of x squared log of 2x dx. Okay, and if we can evaluate this, then we're finished. All right, so we have a product, we have a log, so we must use by parts, and we can write down what our u is straight away. Okay, so if I go straight to it, remember we have the natural log in there, that trumps the power of x, so we take the natural log of 2x as our u. So u is going to equal the natural log of 2x, like that. Okay, that means my dv by dx is going to be x squared, so again I'll state that straight away. Okay, and then we can go straight to du by dx and v. So just remember, of course, if you can use the chain rule for this, but if you remember from class, when you differentiate the natural log of some constant multiplying x, the constants will cancel because it would be the derivative over the function itself, so you'll just get 1 over x again. But please check that if you wish to, if you're not convinced by that. So du by dx is going to be 1 over x. Okay, and then v will be the integral of x squared, which is year 1 integration, so add 1 to the power and divide by your new power. There we go. Our ingredients are done. So let's go straight to evaluating R. So I'll just partition that off. So we've stated the integral already, so I can put that's going to be equal to, so it's going to be uv, so that's going to be x cubed over 3 multiplied by ln of 2x. Okay, subtract the integral of v du by dx. Now if you just look at what we've got here for v and du by dx, I've got x cubed in the numerator and 1 over x or what I should have said was x in the denominator for du by dx. So the power of x here, or a power of x, is going to cancel. So when I multiply them together, I'm going to be left with x squared over 3 and then dx. Okay, now then, that would be a standard integral, okay, without limits. We are integrating between 0.5 and 1. Now, when we use by parts, you'll notice on the right hand side there is a component or a term that is already integrated. It doesn't have the integral symbol because it's already been done. So the uv can just be evaluated between your two limits directly. So what we do is we'll put big square brackets around that term, like so. That's a bit too big, I think. Okay, and that will be between 0.5 and 1. And again, that doesn't look like a 0.5 either, does it? Let's get my rubber. Need a manicure. Okay. Alright, so that needs to be evaluated. Now, also we have an integral to perform, so that needs to be evaluated again between 0.5 and 1. I hope you can read that. Alright, so let's move straight on to the next step. So there's nothing else to add other than we just have to perform the calculation. Okay, so before I evaluate this, I'm going to perform the integral for the right hand term. So that's going to be x cubed over 3 ln 2x between 0.5 and 1, subtract. Okay, now the integral of x squared is x cubed, add 1 to the power, divide by the new power. I already have a 3 in the denominator, so that's going to give me x cubed over 9. And that will be evaluated between 0.5 and 1. Hope you're happy with that. Okay, so let's plug the numbers in. So we have two sets of limits, if you like. Alright, so if I plug 1 in to this, I'm going to have 1 cubed over 3, so that's just going to be 1 over 3 ln of 2 times 1, which is 2. Okay, now the second term, if I plug 0.5 into that, that's going to be 0.125, an eighth over 3. But I'm not too interested, because if you look at the second factor here, the ln of 2x, that's going to be ln of 2 times 0.5, which is ln of 1. And we know that ln of 1 is just 0. So I'm just going to be subtracting 0 within that limit. Okay. Then we're going to subtract the second set of limits. Now that's going to be, again, 1 cubed over 9, which is just 1 over 9. Okay, and what I'll do, just for safety, I'll put all this inside a second set of brackets, simply because we are finding the difference and we don't want to get our signs wrong. Okay, so that's the first limit evaluated, which is the upper limit. So now I subtract the lower limit, substituted into this, and I'm going to convert this into fractions. So I'll just talk you through it. I've got 0.5 cubed. That will give me 0.125. So that's basically 1/8. Now I've got 1/8 divided by 9, so that's going to give me 1 over 72. Again, just verify this on your calculator if you're not convinced. Okay, and I will close the large green bracket now. Okay, and we'll just put everything together. So my final answer is going to be the following. So it has to be exact. I haven't mentioned that previously. The answer must be exact, so I need to keep it in log form. So I'm going to have 1/3 multiplying the natural log of 2. Then I'm going to be subtracting 1 over 9 and then adding 1 over 72. Now if I do that, I could convert all this into 72ths if you prefer, but that's going to just leave me with the following. So that's going to subtract 7 over 72. Again, if you wish to put some more working out in there, you can. All right. Okay, so there's the answer. That's the value of r, and we're finished.